right, we are going to do another day of 11.4, which is calculate, well, mostly it's going to be conditional probabilities, but just general probabilities using a what's called like a tree diagram. And it's pretty useful for, especially for conditional, not for conditional, for dependent probabilities. So like a really quick example that like, for any of you that have ever played poker, like I thought a lot about like, what are the chances you get dealt at least one ace in the game of Texas Hold'em, right? And so the way you would actually do this is with a tree diagram. So you could make like a branch, and like this could be your chances that the first card is ace. So it would be like first is ace, right? And so basically like there's 4 aces out of 52 cards, right? So your chances that the first one is an ace is 4 out of 52 along one branch. And then your chances that you don't get an ace then would be all the other cards, which would be 48 out of 52. Okay, so you could start like a tree diagram like that with your chances you get ace. I guess I could label these. This would be the pass where I got an ace. Here's maybe a better way to label it. Here's our first card. You have a 4 in 52 chance of getting an ace, and then a 48 out of 52 chance it's not an ace. Okay, and then we're going to draw branches for the second card coming off of those points, right? So if I drew a little dot here, okay, so now that our first card was an ace up top, we could get a second ace, or we could get a no ace here. Okay, and so these probabilities are different if we got an ace the first card or if we didn't get an ace, right? So these pass again would be second card ace and no ace. So these second branches are really the second card coming here. Sorry for the poor handwriting again. All right, so if we got an ace on the first card, there's only 3 left out of 51. So the chances we get an ace on the next card would be just 3 out of 51. And the chance that would be no ace would be all the other ones, 48 out of 51 that aren't aces. Okay, and then the probability of an ace down here is different because we didn't get an ace the first time, so there's still 4 left, and there's still 51 cards total. And then here, the chances it's not an ace is all the other cases, so there's 51 cards, and then there's 47 non-aces because we got a non-ace on the first one here. Okay, and so then the probability that we get at least one ace is all of these dots. This one has 1 ace, actually has 2 aces. This one has an ace on the first card. This one has an ace on the second card. Okay, and then this one we didn't get an ace. Okay, so what I got to do is find out the probability for these 3 dots, and these are and. So like this dot up here is getting an ace and an ace. This one would be getting an ace and no ace. This would be no ace on the first card, ace on the second card. So see if you can just do this first dot. Maybe pause the video and see if you remember how to do an and probability. Okay, so the answer is for and, you're going to multiply the individual ones. So my first card, my chance was 4 out of 52. So my chances of getting an ace on the next one is 3 out of 51. If you multiply those together, you get 12 out of 2,652. So the chance you're getting 2 aces is not great. But let's look at this dot, an ace and then a no ace. So I would do 4 over 52 times 48 over 51. So the denominator would be the same, 2652, and then just do 4 times 48. All right, so we'd have 192 out of 2652 for this dot, and then this would actually be the same thing. It'd be slightly different setup, but 48 times 4 would still be 192, and 50, should say 51. This should have been a 52 here, sorry. So it'd be 52 times 51 would still be the 2652. So my chances of getting at least one ace would be add up all these 3 together. So the denominator would be 2652, and then add those numerators. 396 out of 2,652, and then as a percent, if you're interested, this is actually kind of interesting. It comes out to be about 15%. So the chance you get at least one ace is 50, which is really surprising. I would have guessed lower than that, but according to this calculation, looks like about 15% chance of at least one ace. So this is what we call a tree diagram, and it works really well for like conditional probabilities where these conditions in the second part depend on what happened on the first part. All right. So let's do another example. And we're going to draw the tree diagram first and then try to answer all of these questions. Okay, and so you really just got to draw the diagram and make some sense of it. This is rigorous data I calculated on my my very illustrious dating career here. So 40% of my girlfriends are crazy. That sounds about right. 25% of the crazy girlfriends end up leaving me. 90% of the non-crazy girlfriends end up leaving me. Because of course, if they're non-crazy, then they should leave. So anyways, we want to calculate all these probabilities with a tree diagram. So I have a little bit of hard time fitting this all on my screen here, but I want to draw the tree diagram down here and then try to reference it when we do the questions. Do my best to try to fit it all in here. Okay, so when we start off, we know about what happens if they're crazy or non-crazy. So we want to actually split initially like that. So I'm going to split them into crazy and non-crazy girlfriends. And again, it's not going to fit here, but I know that, let's label these. So we have crazy and non-crazy. All right, and so 40% are crazy. So I'm going to label this 40%. And then you kind of have to infer that the non-crazy would be then 60%, right? If 40% are crazy, then 60% are non-crazy, all right? And so from here, then we've got to draw a couple more branches, right? Because the crazy and non-crazy, some will stay, some will leave. Same thing with the non-crazy, some will stay and some will leave. Okay, so hopefully you can sketch this out and then pause the video and draw the rest of it using that data. Right, so see if you can fill in the other parts of it. All right, so when they're crazy, so 25% of the crazy girlfriends end up leaving. So out of the crazy, we're going to label leave, and only 25% leave. Sadly, I wish more would leave if they're crazy. But and then so these are the ones that would stay then, and then you have to infer if 25% left, then the other 75% must have stayed. Okay, that probability is different for the non-crazy, so we can label leave and stay again, and then we just got to look back in the question. So out of the non-crazy, 90% leave. Okay, so we're going to have 90% up here leaving. That means only 10% staying. Okay, so the next step before we calculate all these probabilities in orange here is let's do the dots. So if we can just take these dots, and these are all the and probabilities, and you get them by multiplying the branches, right? Because and you just multiply along the way. So if I do 40% times 25%, that would be 10%. So 10% are crazy and leave, and then do 40% times 70%, 75%, that would be 30%. And then 60 times 90 would be 54%. And then the last dot, 60 times 10 is 6%. Hopefully that would be my wife here that are non-crazy and they stayed. Hopefully that would be how it worked out. Okay, so now these are all the probabilities. So every girlfriend fell into one of these four spots. So this should add up to 100%. And then we're going to use those dots largely to answer the rest of these questions. So again, I have a hard time getting this all to fit, so I'm going to try to move it up as much as I can. Fit it in here, our tree diagram. Okay, so the chances a girlfriend leaves me, right, that should almost be 100%, but amazingly it's not. So let's look here. So the leave, so actually see if you can interpret this. What percent left? Okay, and the answer is it's just these two dots, 10% and 54%. So if you add those together, that's 64%. That seems about right. Okay. So then non-crazy and stays. Again, you just have to interpret this. So I'm going to give you a chance. What's the oops, I didn't want to do all that. Non-crazy and stays. Okay, so non-crazy stays is just one of the dots again. So non-crazy stays here, right? So just follow that non-crazy stay branch, and that's just 6%. Be my wife. Okay, and then crazy and stays again is just one of the dots. So crazy stays is that dot there, 30%. Okay, and then the conditional probabilities is where it gets really tough. So we want to do probability they left given that they're crazy. Okay, so when you do a conditional probability, what normally happens on these tree diagrams is two of these dots are going to make up the denominator. Because we're saying given that they're crazy, so the crazy goes on the bottom. Right? So out of these dots, these are the two dots where they were crazy. So our bottom number in this probability is 40%. And I'm going to read it one more time. Probability left given that they're crazy. So here's our 40% crazy. And out of those crazy, the ones that left were the 10% up here. Okay, so the probability that they left given that they were crazy was just 25%. That was actually kind of given to us in the question, but if we read it off the T diagram, it would look like that. Okay, and that's how all of these are gonna work out. Is the bottom will be two of the dots, and the top will be one of those two numbers. So the probability they're crazy given that they left me. So let's highlight our left ones. So see if we can figure out which two dots represent where they left me. Okay, and that's these two spots, right? Those are both the leave spots. So that's 64%. Okay, and out of the 64%, which ones are crazy? Well, that would be this dot up here. So out of those 64, just out of these two dots, the ones that were crazy ones were 10%. So you could divide those two. I'm not actually going to do it just to save time, but if you divide those, that'll get you the probability they're crazy given that they left me. All right. So pause the video and see if you can do this last one on your own. Right? If not, I'll have a second video coming here that you probably want to go through. But if you feel comfortable doing this, then you should be okay. All right, so probability that they're not crazy given that they stayed. So I'm going to highlight my two stayed dots. So those are those two dots. So only 36% stayed if I add those together. And then out of those ones that stayed, which were not crazy, that would be this one right here. Right, those are the non-crazy stays. So if you divide those out, I believe that comes out to be about 1/6. The probability that they are not crazy given that they stayed is just 1 out of 6. Right, so on the conditional probabilities, two of the dots will make up the bottom, whatever is here, sort of, that'll make the bottom part of the probability. That's what you're looking at, and then out of those two dots, pick one of them to be the top. Okay, and like I said, I'm going to do one more example. Actually, maybe let's not do that. I can probably do it right here, actually. So here's one that involved juniors and seniors and whether or not they're employed or unemployed. And so they already created the tree diagram for us, which kind of helps, but we just have to answer these probabilities. So if you feel like you're struggling on this, watch the next video and I'll go over this example. If you feel okay, then you could just start on the assignment. All right, thanks for watching.